we were looking at probability rules. We started talking about the basic rule of probability, and then we looked at complement rule, then we looked at problems involving or. Now let's look at sorry now let's look at just a sec. So now let's look at problems involving and. So this is the fourth that we want to look at, problems involving. Now, here the ideas are probability of A and B. So if you want to find the probability of A and B, just like we talked about in the previous video, with OR always means union. So here we need to keep in mind and means intersection, right? So in probability, when you see OR, that means union, and when you see and, it means intersection. And so we can write this as probability of A intersection B. Now, a couple of things to note here. We can also write this as probability A comma B, right? So comma means and or intersection, right? So if you want to write probability of A and B is probability of A intersection B, which can also be written as probability A comma B, with the comma means and or intersection. Now this is probability of both. So when we talk about probability of A and B or probability of A intersection B, this is the probability of both A and B occurring at same time. So this is the probability of both A and B occurring simultaneously. So this is a joint probability of A and B. Now how do we find this? Now probability of A intersection B, we can find it either as probability of A given B into probability of B, or probability of A intersection B is probability of B given A into probability of A. Right, so this is what we call the multiplicative rule, and both give us the same answer. So depending upon what conditional probability you have, you can find it either way. Both will give the same answer. So the idea is this: you can either find probability of A intersection B as probability of A given B into probability of B, or as probability of B given A into probability of A. So it depends upon what probabilities are you given. Both will give you the same answer. So now note that this formula. Now note something. Note that this formula is simply the conditional probability formula rearranged. So multiplicative rule just comes from rearranging the conditional probability formula. Simply the conditional probability formula rearranged, right? Because you have probability, conditional probability formula is probability given B is probability of A intersection B divided by probability of B. And we know probability of B given A is probability of B intersection A, and probability of B intersection A is the same as probability of A intersection B, because we're just looking at the probability of both of them occurring at the same time. So the probability of A and B and probability of B and A are the same thing, right? So if you notice over here that essentially the formula for multiplicative rule that we've written is just the conditional probability formula rearranged, right? Over here you can just make probability of A intersection B the subject, so you get this. It's probability of A into B, probability A given B to probability B. Here you can make probability B intersection A, which is the same thing as probability of A intersection B. We're just looking at the probability of both of them occurring at the same time. So this is just probability B given A into probability of A, right? So this is the multiplicative rule formula comes from rearranging the conditional probability formula. Now this is in general that whenever you want to find the problems for probability for a problem involving AND, so we know it's probability of the intersection, and you apply the multiplicative rule. Depending upon what conditional probability you're given, you can use either one of these. Both will give the same answer. Now let's look at a special case. Now special case. If A and B are independent events. Now we're looking at a special case where A and B are independent events. Now let's first look at what do we mean by independent events. So let's recall. And if occurrence of event A, if occurrence of event A does not change probability of event B, then A and B are independent events, right? So occurrence of event A does not change probability of B, then A and B are independent events. So if they're independent events, we know the conditional probabilities are the same as unconditional probabilities. Probability of A given B would be probability of A, and probability of B given A is probability of B. And because it's independent events, the occurrence of event A will not change probability of event B. So probability B given A is probability of B. Similarly, occurrence of event B will not change probability of event A. So probability of A given B is the same as probability of A, because occurrence of one event does not change probability of occurrence of the other event. Then they're said to be independent, right? So if they're independent events, then we know the conditional probabilities are the same as unconditional probabilities. So the above formula simplifies to, so the above multiplicative formula, or the above formula, so the multiplicative rule simplifies to, so in this case we can simplify so the multiplicative rule simplifies to probability A intersection B is just probability A, probability B. Because like we looked at, the multiplicative rule was what we looked at. If you want to find, one way to do it is probability intersection B is probability of A given B into probability of B. Or we said you can find it like this: probability of B given A into probability of A. Both give same answer. So now, since the independent events, the conditional probability is same as unconditional probability. So in the special case where A and B independent, probability of A given B is probability of A. In the special case, like we said, where they're independent, this is just probability of B. So when they're independent, the multiplicative rule just simply becomes the product of the individual probabilities, right? So or more generally, if you look at more generally, here we're looking at just two events. So, but if you look at more generally, probability of A1 intersection A2 intersection so on and on intersection AK is just the probability of A1 times probability of A2 so on and on till probability of AK if A1, A2, AK are independent. So whenever you know some events are independent, the probability of the intersection can just be found as the product of the individual probabilities. So multiplicative rule in case of independent events simplifies to just multiplying the individual probabilities. As a multiplicative rule, just simplifies to multiplying the individual probabilities. So now let's note a few things. So like now we said, in general, if you want to find the probability of intersection, you apply the multiplicative rule. And in the special case with independent events, the multiplicative rule just simplifies to multiplying the individual probabilities. Now two things that you want to note, keep in mind, probability of A and B is the same as probability of B and A. So probability of A intersection B is the same thing as probability of B intersection A. We are talking about the probability of both A and B occurring at the same time. Now, and also like we talked about the multiplicative rule, we just looked at that for two events, right? Probability of A intersection B is probability A given B into probability of B, or probability of B given A into probability of A. But multiplicative rule is not necessarily for just two events. You can't extend it to more than two events as well. It's not necessarily just for two events. We can extend into n events. We can extend it to n events. So now multiplicative rule for more than two events. So let's just look at that multiplicative rule for more than two events. So if I say I want to find the probability A intersection B intersection C and I want to apply the multiplicative rule, so we can write it as probability of A into probability of B given A into probability of C given A intersection B, right? So this is the probability of intersection of three events. Similarly, you can find the probability of intersection of four events. And this would just be probability of A into probability of B given A into probability of C given A B into probability of D given A B C and so on. So you can't extend the multiplicative rule to more than two. So this is just AB. What I've written over here is just the intersection of A and B. Similarly, this is intersection of A and B. This is intersection of A, B, and C. Alright, so we can extend the multiplicative rule to more than two events as well. So if we just summarize what we have done, in short, in general, if you want to find probability A intersection B, this is just probability A given B into probability of B, or probability A. In general, this is how you find the probability of intersection equivalence. Probability B given A into probability of A. Right? In general, you can find it like this. Both give same answer. This is the multiplicative rule for two events. Both give same answer. This is multiplicative rule. Only if A and B are independent. So in general, you have to apply the multiplicative rule to find probability of intersection only if A and B are independent lines. So in the special case where they are independent, where occurrence of one does not affect probability of occurrence of other, then you can say probability A intersection B is probability of A into probability of B, and you can write it as a product of individual probabilities. So in general, whenever you want to find probability of intersection, you have to apply the multiplicative rule. But in this special case, where they're independent events, then you can write the probability of the intersection as the product of the individual probability.